Hey guys, what's going on? So what you're watching here is a clipped video from a whole video that you'll be able to access if you become a member on Patreon or if you become a member on my YouTube channel. These videos are relatively difficult to make because I'm using multiple sources to compile all the information together. And so with your contribution, I'll be able to make more content as well as create exclusive content for those of you who are really invested into this channel, who really want to understand a lot of advanced physics and life sciences. So with that being said, make sure to hit the like and subscribe button. Make sure to go onto the Patreon page and you can contribute there. You can also become a member here on YouTube. So let's now get into the topic. Hey guys, what's going on? So today we are going to be covering homology. We're still on the topic of Chern Simons theory, but we haven't really talked about Chern Simons theory yet, primarily because we need to establish a lot of this mathematics first, because fundamentally Chern Simons theory is a topological theory. And so we're covering the math, then we're going to cover the electromagnetism, and then we're going to put things together. But the idea here now is that we're going to take approximately 2, maybe 3 videos on the concept of homology. Then we'll get into the concept of cohomology, and then we'll be able to go from there in invoking more physics. So let's talk about homology. We're going to start off by talking about the complex, or the notion of a simplex. So homology is interesting. So last time when we talked about homotopy, we talked about loops. That was one way we were able to define holes in things, okay? The next thing we want to do is we want to talk about the shapes themselves, right? So topological shapes themselves. And what we're going to need this concept of a simplex. And a simplex really is this thing that if we consider all the independent variables in some parent space to equal 1, this in one dimension, it's going to be a single point, okay? So it's our zero simplex. In 2 dimensions, it's going to be 2 points, right? And not 2 points, right? This should actually be, if we omit these guys, actually, these are 0 simplexes. This guy here is our 1 simplex. Okay, that's the line between the line that you could fill, the straight line that you could fill between the 2 points. And then we had our 2 simplex. So that their 2 simplex is the space that you fill between the 1 simplexes. Okay. So, and these guys, so that's what you get when you have all your independent variables add up to 1. You have this area. So we can sort of think of a 2 simplex, or we can sort of think of a 1 simplex as being the boundary of a 2 simplex. We can think of a 0 simplex as being the boundary of a 1 simplex, and that's really how we want to think of this. And specifically, we could say, well, an n simplex is a collection of n plus 1 minus simplexes, and the way we do that, again, is n plus 1, n minus 1 simplexes. So if we're looking at a 1 simplex, for example, this is going to be a 0 simplex. It's going to be 2 0 simplexes, right? So 1, 2. The result is that an n simplex is n-dimensional. What that means is that our 1 simplex is a 1-dimensional line, our 2 simplex is a 2-dimensional area, and so forth. So we could take a collection of n minus 1 simplexes then and create an n simplex. And we do that in the following way. So suppose this is our n simplex. Our n simplex, to say, is a 1 simplex. Well, that's going to be in our parent space, right? So our x in our parent space is just going to be a 1 simplex, right? So if this was 1, then we're looking at something that looks like this. Well, it's in a 2-dimensional plane, so our m is going to be 2. But then the collection of points that make up the n simplex is going to look like this. We have a point here. So we have a point here and a point here. So we're going from 0 to 1. Right, so we're summing at 0.0, so we could sort of think of this as P0 and P1. All right. We can denote an n simplex over n plus 1 points. I'll erase this really quick. we can denote our n simplex over n plus 1 points in this way then. So our n simplex, our 1 simplex then, is going to be n p0, p1, right? So the line between point 0 and point 1. We need to make our terms very clear. The n simplex is the space that is filled between the vertices and the boundaries with, and we can see this with an image. So our 2 simplex, or so our 1 simplex again is the boundary of our 2 simplex, and our 0 simplex is the boundary of our 1 simplices. And all of these together make a simplical complex. In order to prevent a simplical complex like the following, we say that the intersection between each complex is the face, or equal to each complex. So we're saying that the intersection is the whole complex itself. You can sort of think of it as that, in that way. Or you could sort of think of this as, well, the intersection is the face, the black face here, between the 2 and the 1 simplex. And we avoid, when we do that, we avoid a situation where we have one simplex just pointing out like this. All right. Simplices also have an orientation. So we can define P0, P1 as having this orientation, and P1, P0 as being the negative of that orientation. So we write this. We can also write for 2 simplex, so we have 0, 1, 2. Well, that's going to be the same thing as 2, 0, 1, right? So we have 2, 0, 1. Well, it's also going to be the same as 1, 2, 0, right? So there's our 1, 2, 0. And then we have our 1. Hey guys, thank you for watching this shortened clip from a longer video. If you want to get the longer video, again, you can become a member of the YouTube channel here, or you can go into my Patreon page where you can become a member there. All the tiers should match up in price range, and yeah, if this is the type of topic you're interested in and the type of topic you want to contribute to, then please become a member, hit that like and subscribe button, and I'll see you guys in the next video. Bye.